The next type of channel distortion that we want to discuss is channel distortion that's caused by nonlinearities in the channel. And so if we really want to understand this, this is really a bit beyond the scope of this course. And that's because when you get into having nonlinearities in your channel, you're no longer dealing with the same types of signals and systems that are a little bit more typical to discuss in an undergraduate course. However, we can easily get some idea of how these nonlinearities could cause big problems with our distortion. So let's imagine that you have some input to your system, GT, and in order to get the output, your output goes through some nonlinear function, f of t. So let's say this function, f of t, we don't know what it is, but it's nonlinear. So when we take our input, it's going to go inside of this function. This f function is going to be nonlinear, and it's going to cause us some big problems. So our input, g of t, enters this nonlinear function, and now we have a nonlinear output. And we can model this nonlinear output in something that's pretty common to do for engineers is we can use a Maclaurin series, which is kind of a special case of the Taylor series. So we'll model our channel output using this Maclaurin series. And we can see that the Maclaurin series has this kind of chain of derivatives that we can approximate the function as. So we're going to consider our output modeled as a Maclaurin series. And if we do that, then we'll say that our output is y of t, like this, and our input, remember, was this g of t function. So we now have an approximation of our output written as a series, a Maclaurin series, in which this g of t input appears over and over, but at progressively higher powers. So first it's just g of t, then it becomes g squared, and so on until you're taking this out quite large and you have all the way up to g of k. So what's the big deal if our output begins to look like this? So what's the big deal if we have this nonlinear output where our input begins to have these progressively higher powers? Well, each time that you get this higher power, these actually are going to correspond to higher bandwidths when you consider the convolution property of the Fourier transform. So if you go back to your Fourier transform table, what you'll see is that when you have this first power, it will have some bandwidth b, but when you take it to the second power, that's going to double the bandwidth. And when you take it all the way out to the kth power, you're going to have a very large bandwidth. Now, of course, these coefficients might change, they might get smaller, and so you might have a very small coefficient multiplying by this, but nevertheless, what you've done is you've taken your input, which had just the bandwidth b, and by passing it through a nonlinear channel, your output now contains a very, very large amount of bandwidth, maybe infinite. And from what you should remember from the beginning of this class is that bandwidth is essential. And if you're going to take your input spectrum and turn it into this gigantic output spectrum that's k times larger, it's going to include all these new frequency components, and that's going to cause you problems down the road.